Hey guys, so we are looking at solving real life examples with systems of equations, part two, so video number two. Yesterday we worked on just general type and then mixture. And today we're looking at problems that you're going to be able to use probably in all of your science classes, as well as math, and they're distance problems. So first I want to talk about the formula for distance. In math we use the formula D equals R times t. Now, we're not talking distance in the coordinate plane. We're talking just distance, general distance questions. D equals distance, R equals the rate, okay, and t is the time. All right, so I want you to think of rate for now as a speed. And if you go into physics at any point, the formula, they just change it because rate is really the velocity of something. So the formula might be D equals V times T. But it's the same formula. So we're going to use rate to think, we're going to think of rate as the speed of something. All right, so first we're going to look at examples when things are going in the same direction. So here we have a train. It leaves DC traveling west at 80 kilometers an hour. 1 hour later, another train leaves DC on a parallel track traveling at 120 kilometers an hour. How far from DC will the trains be when they meet? Okay, so first of all, when they meet, so here's the first one, and here's the second one. They meet when their distances are equal. Okay, so that's something, for you to really understand. All right, but we have to figure out what our unknowns are. I like the D equals T problems because you can actually just make a little chart for yourself to help you with what you have and what you don't have. So D is always our distance. R is our rate. And T, I want you to think of these problems as T is the time moving. You're going to see in a second why I say that. Time moving. In this case, time the train's on the tracks. All right, so I make a chart. D equals R times T. I put that at the top and I fill in for the two trains. So I'm going to call, on the left side, I'm going to say the first train and the second train. Okay, because they left at different times, I have to look at each one individually. So the first train leaves DC traveling west at 80 kilometers an hour, so that's the rate. And the time is unknown because we don't know what time he left. And his distance is unknown. So remember, it's a system, so we are going to have two unknowns. 1 hour later, listen up because this is the hard part. Another train leaves DC. Well, if T is the time moving and this train left an hour later, then this would be T minus 1 because he's going to be on the tracks, so to speak, moving 1 hour less than the train that left first. His rate's 120 kilometers an hour, so he's going faster. And again, his distance is unknown. All right, so there are my two equations. My first equation, D equals 80T. My second equation, D equals, now I'm going to distribute since it's multiplication, right? So 120T minus 120. All right, system of equations. It's all set up for substitution. I have this D with a coefficient of 1. I can substitute 120T in right here. So I get 120T minus 120 equals 80T. I'm going to actually bring the 80 to the left and the 120 to the right, so I'm going to get 40T equals 120. I'm going to switch colors because that's not looking so good. Divide by 40, and so T equals 3. But remember, the question says, how far from DC will the trains be when they meet? Well, we know the time they're going to meet is 3 hours after the first one leaves, okay? Or 2 hours after the second one leaves. But now we got to find the distance. So I'm going to plug it into the easier of the two equations. So 80 times 3. So a distance of 240, and these were in kilometers. So kilometers. Okay? All right. I want you to try the next one. So I want you to follow that method. A car leaving Hartford, traveling north at 56 miles an hour. 2 hours later, another car leaves traveling 84. When will they meet? So D, remember, is distance. T is time driving. R is the rate or the speed, okay? We put D equals R times T, and we have, how about the first car and the second car? All right, I'm going to have you press pause, and then you can come back and check your answer. So go for it. Press pause and try it. All right, so hopefully you recognize that D was unknown. The first car was going 56 miles an hour for an unknown time. The second car, we don't know the distance, but we do know the rate was 84. And he left 2 hours later, so this case would be T minus 2. My two equations then would be D equals 56T and D equals 84T minus 168, because I want to make sure that I'm multiplying, so I would distribute that 84 through. Great place to use substitution, so I'm going to substitute this in for D into the first equation. So 84T minus 168 equals 56T. So 28T equals 168 by balancing the equation, and T equals 6. I go back to the question being asked, when will they meet? They will meet 6 hours after the first car leaves. So always making sure that we answer the question being asked for us, right? So hopefully that one wasn't too bad. All right, so those are the easy ones. The harder ones are when we're dealing with things that involve currents or winds. So a couple things I want to make sure we understand. I want you to understand that upstream and downstream. Upstream means you're going against the current. So it's going to always be a subtraction prop. We're going to subtract the current, okay? And we're going to use C for current. Okay? Downstream means that we're going with the current. So we're going to be faster. So we're going to add the current. It's going to help us. All right, tailwind. So we use W to indicate the wind rate. So currents rate and winds rate. So a tailwind is pushing us faster because it's pushing us from our tail. So we're going to be going faster. It's pushing us. So that's going to be plus W. Whereas a headwind is going against us. It's making us slower. It's making us slower. So that would be minus W. All right, so these are what we do for currents and winds. We also need to be aware that when I ask for the speed of something in still air or still water, that's the R that we use in the distance equals rate times time. So this variable is R, okay? Still air, that means there's no wind or current, and we would be adding the wind or the current. All right, so let's look at our first example. So we have a motorboat. It took 3 hours to make a downstream trip with a 6 km/h current. The return trip against the same current took 5 hours. Find the speed of the boat in still water. Okay, so I want to make sure that I get my variables going. Okay, so I'm trying to find the speed of the boat in still water. That's R. So speed of boat. And I don't know the distance. It says a trip, so that's another unknown for me, distance. Okay? All right, so when I label my diagram, I'm going to label the downstream and the upstream. So here I'm going to put down for downstream, and here I'm going to put upstream. And again, we're still putting D equals R times T. All right, so this is where I have to get a little careful, all right? So I'm careful because I have to add the downstream trip and I have to add the currents, okay? So my distance was unknown. My rate, I know the current was 6 km/h, but I'm looking for the speed of the boat. So I have the boat plus the current of 6 and a time of 3. Coming back, again, I don't know my distance, but I know that I'm going against that same current. So that would be R minus 6. And that time it took us longer because we were slower, right? Which is 5. All right, so we have an expression here. Remember, we're multiplying, so I'm going to do D equals 3R plus 18, and D equals 3R minus 30. Again, great place to use substitution. So 3R plus 18 equals, oh, sorry, this should be 5R. 5R minus 30. Sorry about that, guys. All right, so I'm going to subtract 3R, and I'm going to add 30. And I get 48 equals 2R, so R equals 24. So the speed of the boat is 24 kilometers an hour. And that's all it's asking me to find. I don't need the distance, but I could find the distance if I wanted to by multiplying 3 times 24 and adding 18 to it. Okay? All right, so let's move on. An airplane flew for 5 hours with a tailwind of 25 kilometers an hour. The return flight against the same wind took 6 hours. Find the speed of the airplane in still air. Hint, the distance is the same in both ways, so similar to the last one. I want you to try it, and we're going to go over this one in class to make sure you got it right. All right, harder. What if we're missing the wind and the rate? Well, let's look at this one together. A jet can travel 6,800 kilometers distance from New York. Actually, it should say between. Yours probably does. Between New York and Paris. In 6 hours and 48 minutes. Okay? With the wind, which means a tailwind. The return trip against the same wind takes 8 hours. Find the rate of the jet in still air and the rate of the wind. So my unknowns in this case are R, the rate of jet in still air, and the rate of the wind that's either helping or hurting me. All right, so I'm going to put, in this case, I'm going to put with the wind and against. I'm going to fill in my D equals R times T chart, D equals R times T. And I'm going to plug in what I have. Well, the distance from New York to Paris is 6,800 kilometers. So I'm going there at 6,800 and I'm going back at 6,800 because it's the same distance, okay? The time there is 6 hours and 48 minutes, although we need to write that as a decimal or a fraction. I prefer the decimal. So 48 of 60 works out to be 0.8. 0.4 is, when you simplify it, it's 0.4. So, 0.8. Okay. So my time is 6.8 hours. Whereas the way back, against the wind, it was 8 hours. So it should take longer because it was the wind was making me slower. All right, but on the way there with the wind, I would have R plus W, and on the way back, I would have R minus W. All right, so we multiply, right? Because these are expressions. So we get 6.8 R plus 6.8 W equals 6,800. And we get 8R minus 8W equals 6,800. Now, here's the big thing, really important. You don't want to work with these numbers, and I see that 6.8 is divisible on the top. So I'm going to simplify both my equations by dividing the whole thing by 6.8. I'm going to divide this one by 6.8, and I'm going to divide this one by 8. So my new equations work out to be R plus W equals 1,000 and R minus W equals 850. Look how nice that is. It's now set up for us to beautifully do elimination. I don't even have to multiply. So you always want to simplify if you can, okay? All right, so I get 2R, the W's cancel. 2R equals 18, oh, so this was 1,000. 1850. When I multiplied, I forgot the 0. and I divide by 2, and so R equals 925. That's the rate of the jet, 925 kilometers an hour. All right, now I got to get the rate of the wind. Well, I'm going to plug it into this equation right here. So 925 plus the wind has to equal 1,000. So that makes W 75. So the wind was 75 kilometers an hour. All right, guys, that was a lot today. Great job. Again, these D equals R times T questions don't have to be hard, but think about making yourself a chart every time you're working with distance problems to make them easier. Okay? Have a great night.